Okay, here we are again doing CLEP calculus practice exam questions from practice exams that I found online. In the previous video we finished that first one. We're going to start on that second one again. Again, are these links still good at this point or not? I don't know. They may or may not still be there to still download. I can't promise that, but we are going to get into it. So we know this is the other test because somebody marked extremepapers.net at the bottom of each page. That's not even where I got it from. It may be where they got it from. The other thing is, between these two tests, there are a lot of duplicated questions, like the exact same question. Not even different numbers, not even the answers in a different order, just copy paste exactly the same. So we're not gonna go over any of the ones that we've done before. So that cuts out about half, a little over half of what this test otherwise is. But that remaining half is still good practice. So we are going to hit those and just skip the ones that we've already seen. Okay, so starting out at number one here, pretty simple. F of x is negative 2x to the negative third power. What is the derivative? So basic power rule, take the exponent, bring it down, multiply, and then subtract 1. So negative 2 times negative 3 is a positive 6. Negative 3 minus 1 is a negative 4. And response C is there. Okay. Number 2. What is the limit as x approaches 3 for 1 over x minus 3? So another one of those where at that value we get it and we turn into a divide by 0 type situation. And the trick we're going to use for this is, given that this is a pretty simple one, you may recall from earlier math classes having seen a y equals 1 over x, where you get basically something like that, where, because at the small x it gets very large, so it doesn't have a gap in the graph like a lot of the limit problems we've seen so far, but rather you get a asymptote for this one at x equals 0, and so it zooms off down this way to the asymptote and then comes back down this way. So we're going to suspect this might be kind of like that, and we can think about it that if we think of x equals 2, then that's going to be 1 over negative 1, it's a negative value, but at x equals 4, it's going to be 1 over positive 1. So that already tells us that from one side of the relevant value, x equals 3, on one side we have a negative, on the other side we have a positive. So we're thinking it's not going to match up. It's not going to be one of those where there's just a simple gap in the graph that you could fill in, but it's going to be one of those where it's going to zoom off and zoom back. So we're going to say it is E, non-existent. And for this group of questions, this is taken from, well, it even says right here, calculator may not be used. But just to prove it, I'm going to grab the calculator really quick, and we can see what it actually looks like. So we can say 1 over x minus 3, and it totally does that thing. It's just the y equals 1 over x moved over to the right by 3 notches, which is what you get when you just take an x and substitute it with x minus 3. You're just taking the whole thing and shifting it over. So that's how that works, and that's the easiest way to determine with the limit, especially if they don't give you a picture, is to just take a quick sample value close to there, and you can get a feel for, is it coming up to the same point, or is it not? And if it doesn't, and it's a limit from both sides, then we can say non-existent. If we were doing a one-sided limit, for instance, if there was a little plus there, meaning approaching 3 from the positive direction from the right-hand side, then we would actually be infinity, because it's zooming up to infinity. But it's not, it's the double-sided limit, so we're going to say non-existent there. Okay, number 3 and number 4 are duplicates. We did those already, so we are going to move on. And again, number 5 is a duplicate, number 6 is a duplicate, number 7, got a lot crossed out, number 8, here's one we haven't done, number 9, and here's another limit question. These tests, lots of limits. They seem to love the limits. Okay, so what is the limit as x approaches infinity for x squared minus 4 over 2 plus x minus 4x squared? Okay. So what can we gather from this? And again, this is one of those, if we were allowed the calculator, we could graph it out and check it at some very large number, and it would usually for this type of thing, where it's saying as x approaches infinity, there's a horizontal asymptote that the graph is approaching some value as it gets very, very large. But how can we do this fairly quickly? Well, if we think about very, very large values of x, the 2 is not going to be relevant, the negative 4 is not going to be relevant, and even the x is barely going to be relevant. So x squared is going to completely dominate once x gets very, very large. So if we reduce it to just this, and then we notice that we have x squared on top and x squared on the bottom, so those actually cancel out, and it kind of just leaves us with 1/4, and that is negative 1/4. That is indeed the answer, and you could test it out yourself. Grab your calculator, graph it, punch in, set x equal to 1,000 or something, and calculate it out, see what it does. But we can just very quickly get there just using our reason that it simplifies and cancels out, and that makes that a pretty easy one. All right, let's move on to number 10, and this is a definite integral. We're going from -3 to 3, on the absolute value of x plus 2. Okay, so there's kind of two ways to go about this. Kind of a easy way, kind of a hard way. You tell me which one you think is which. But if we think about just x plus 2 by itself, y equals x is obviously just a line like that. And then if we're adding 2, it's going to be 2 up. That's 2. That's going to be negative 2, right, on x and y. But we're asking about the absolute value of x plus 2. So this part is not actually going to be down there. It's going to be up this way. So just one big, diagonal line coming down and then back up again. And then if we think about it, it's asking us to find when it goes from, again, the definite integral is the area underneath the equation from negative 3 to 3. So if we have negative 3 there and the 3 there, and we just kind of think about that. And so we know we can figure what is x plus 2. So if x is 3, then that's going to be 5. And for x of negative 3, negative 3 plus 2 is negative 1, but it's absolute value. It's flipped up to the top. So this is just 1 there. And, they're obviously right triangles, because this distance is 1, that distance is 1, that's 5, and from negative 2 to 3 is 5. So this just actually reduces to a couple of triangles. So the area of a triangle with a side 1, base 1/2 base times height, and that's 5 and 5, 1/2, 5 times 5, so 1/2, and 1/2 of 25, or half of 25 is 12.5, becomes 13. And yes, indeed, we have the 13. And that is the answer. Now, the other way to do this, if you're not going to draw it out, if you're not going to visualize it, I'm going to just do it the old calculus way. We have the definite integral, but there's no, I don't think there's a good way to handle the absolute value there. So we would have to break it up, going from negative 3 to negative 2 for the portion of it that's flipped up, and then add that to negative 2 to 3 of the original version of that. Oh, I forgot to write the dx's, and if you go to the effort of working all that out, a little more math involved. You have to integrate, and then you have to plug in, and I promise you it would still come to 13. You can try that on your own if you want, but when you're pressed for time, if you can envision the graph and you can envision, hey, it's just a couple of triangles, that's all you need. I think it's very deliberately set up to be that simple, or you could use the more proper calculus way if you want, and you know, still going to get you there. Okay. Again, 11 and 12 are duplicates. Those are ones we've done before. So let's see. 13 here also is one we've done before. So let's go to number 14. Selected values of the functions f and g and their derivatives, f prime and g prime, are given in the table above. So we don't have the equations, but they're just giving us what the values would be. If we had the equations and filled in those values, we would get those numbers. We just skip a step. We go straight to the numbers. And so if equation h is the composite function of g of f of g, then what is the derivative of h at 30? Wow, that's interesting, isn't it? Well, remember that when you have a composite function like that, f of g of x, that the derivative of that, this is the chain rule. So the derivative of f of the original g times the derivative of the g. And we want to know what that looks like at 30. So we can think of it as the derivative of f at g of 30 times the derivative of g at 30. And now, what is that going to be? Well, let's look at the table. So for x of 30, g of x is 20, and the derivative of g at 30 is 10. So we plug those in, and it's still the derivative of f, but at 20. And then the derivative of g at 30 is just 10. So now we still have this function. We have to look the derivative of f at 20. Well, we actually have that too. It's in this column. So we go over and look, and it's just 5. So now we have 5 times 10. And that is going to be 50. And 50 is indeed one of the choices. And that is indeed the answer. So, chain rule, roundabout way of going, chain rule by way of no actual equations, but just numbers to punch in, to fill into those values, but the chain rule nevertheless. Okay. And we will move on to the next one in the next video.